Okinawa. So if you want to get the slides, these are the slides for today, the first of several sets of material. We're going to cover a lot of ground between now and 3:30, I think we finish, right? As a result of yesterday's questionnaire, which if any of you all didn't fill it out, you can, but I don't really need it. It's just, I was just trying to get to know everybody. That we're going to talk about the results of that in just a second. As a result of that, I've really kind of shifted directions in the last 14 hours or so and prepared a set of different material than sort of what I had originally planned. So we'll see how that goes. As Arthur said during his talk, we faculty like it when you interrupt us and when you ask questions. Sometimes we may have to cut things off in order to advance the overall agenda, but we like to make things interactive, and in particular, I do. So if you have any questions about anything, just stick your hand up and ask, interrupt, and we'll go on. Let's see. So actually, let's go back and look at those results first. Oh, David, do I need to be sharing this screen in the Zoom or anything? No, you just got the Zoom. Okay, right. So let's look at those results. Where are we? We got 32 responses here. I traveled X kilometers to get here. Woo. Bunch of people who traveled 9,000, 10,000. Apparently some of you all decided it was a competition. So we got 10,000, 10,100, 10,500, 12,647, right? And approximately 14,000. Somebody said 16,000, so they should get a special prize. Who came 16,000 kilometers to get here? Now nobody's willing to own up to it, huh? Right? All right. So IMA, you can answer or check more than one. Lots of people said experimental physicists. I guess, how many total attendees do we have? 50 or 60, so 15 is only a quarter of the people, but it's still the biggest number. 15 people said experimental physicist, another 13 said theoretical physicist, 10 said theoretical computer scientist, and 4 actually checked experimental computer scientist, and I'm curious what an experimental computer scientist is, because I just made that up yesterday. System architect, hardware engineer, software engineer. I am a system architect and former software engineer, and have worked also very closely with hardware engineers over the years. And of course, one person gets extra credit for being the experimental beer drinker. So let's see, most people said you're already familiar with the various notations, which is good. And then these next several things are on a scale from never heard of it to I could teach it. And it seems like everybody is pretty good on teleportation, actually. And then entanglement swapping was tilted a little bit more toward the middle. And so that may actually be worth spending some time going over. And then purification was a little bit lower. So we'll study that a little bit this afternoon. Let's see, Dijkstra's algorithm got a lot of never heard of it, so that's fine. Various people had interesting comments on what multiplexing means. One of the reasons I asked about multiplexing is that when you read different papers from different groups and even talk to different people, you'll get a very different underlying assumption of what multiplexing means. Me being a relatively high-level systems engineer, to me, multiplexing means assignment of different high-level communication connections to the set of resources you've got. But in some cases, it's people literally saying, well, I can get 2 or 3 or more memories to talk to the same physical channel, and therefore that's a form of multiplexing. And that's true, it's just a different definition. And so it's worth checking when you're talking to somebody about multiplexing what their definition is for the particular context you're in. Hongo Mandeldip, a handful of people said they've never heard of it. Well, actually more than a handful, it's pretty good. So we'll see that again later. And a number of people said you're already pretty familiar with it. Favorite type of qubit, a photonic qubit, polarization spelled differently. GKP, shape, time bin, interesting. Favorite type of matter qubit, Same as above. So somebody says photons are a form of matter. That's an argument for Arthur, not for me. I don't have any idea. Tardigrade, that would be. We have another professor who works on tardigrades. That would be interesting. Everybody says they're comfortable with Python, but not very many people have used Qiskit. And Steve Deering's OIST, we'll talk about in a couple of minutes. People said they like the physical layer and the network layer. Only about half of you said you can actually spell TCP/IP, so I'm a little bit worried about the other half of you. The P in IP stands for, protocol. Okay. And the difference between a network and an internetwork we're going to talk about. And then not everybody got all of these last few questions because there were some I had forgotten to put in when I gave it to you all yesterday. SPDC, we will see a little bit about SPDC, but not very much. And the programming languages, I actually entered that into the system wrong, and so I forgot to make it multiple checkboxes. So it goes. Bell state analyzers, we'll be talking a little bit about that, and RFCs, we'll be talking about that. Transduction, unfortunately, I'm not going to get to in the set of talks. I hope somebody will talk about it sometime in the next 10 days because it's really important for the physical systems that we're talking about. Anybody got any comments or questions? Just sort of about what the background is, whether everybody's happy? So we have a pretty diverse background, but the level is actually pretty high relative to where I thought we were going to be. And so let me go back to these slides. As I said, we have a whole bunch of different materials we're going to use over the next couple of sessions. The first thing I want to do is I want to run through this set of slides that are right here, which cover some of that material to help sort of set the right level. This is the first day of 10 days, right, of material. And unfortunately, I have to go home tomorrow night back to Tokyo. I'd rather stay here with you all because I would learn a whole lot of stuff. Plus, there's this fabulous view over here, right? But unfortunately, I am at Keio University. I'm the chair of the Cyber Informatics Graduate School program, and on Wednesday we have guidance for incoming students who are graduate students this fall, so I have to be there for that, unfortunately. So what you're going to see is a little bit of a mix of pretty basic stuff and some very advanced stuff over the course of the next 4 hours. So I don't expect that some of you are going to find some of this a little basic, and then out at the other end, there's going to be stuff probably that everybody doesn't get the first time around. And so you can ask me questions, and also many of the topics that I'm going to skim over will reappear over the next 10 days. And so you'll get a chance to sort of catch up on some of that as we go. So the first thing I actually want to do, so after going through this set of slides, is just 2 weeks ago, David and I and Akihito, who is not in the room at the moment, he's off doing an online meeting or something, and Soon and Mia, anybody else? Joshua, we were in Albuquerque for the IEEE QCE, IEEE Quantum Week 2 weeks ago. And I gave one of the keynotes there, and I worked really, really, really hard on creating that talk, so I figured I would reuse it and give you all a look at that material. Because other than that handful of people, I don't think anybody else was in Albuquerque. Anybody else I didn't name in Albuquerque? Oh, were you there? Good to see you. Good conference, right? You were there. All right, and then so that should take us pretty close to lunch, I think. But before lunch, we might get to actually introduce the hands-on material. So there is some hands-on material today. It's basically a Jupyter Python notebook that covers teleportation, entanglement swapping, and purification. And we'll go through that. So that'll be some hands-on where you all are working, and I'm not just standing up here and talking. So the entire next 10 days is not going to be just listening to people talk, or at least hopefully not. And then we'll end up with some discussion of how we can get towards standards for these things. As I've already mentioned, I am an engineer by trade, And so I'm interested in how we are going to build systems that people can really use and really package things. So that's where we're going to go. And that brings us to the key concept. We want to advance from experiments towards systems. That guy sitting next to me is Dave Farber, who is the grandfather of the internet, who is also a member at the spry young age of 91. He's 91 years old, and still one of the smartest people I've ever met. But I showed Dave some Qiskit code. Qiskit being the IBM Python-based library for quantum computing, which a handful of people said they weren't familiar with. I showed Dave some Qiskit code a few years ago, and he looked at it and he said, "That's not an application, that's an experiment." Right? Well, we want to get away from just doing experiments and being able to build applications and systems that people actually use. So, quick advertisement before we go into it. I've already mentioned QCE. We were there 2 weeks ago. I gave one of the keynotes. We won 2 of the best paper awards while we were there. This is the hall in which those keynotes were held. There were 1,750 people on site and another couple of hundred online participants. So it's now one of the world's largest quantum-related conferences. QIP, of course, is one of the others. Let's see, what else? Well, of course, lots of people go to the APS March meeting with a lot of that. And then, of course, on the business-oriented side, Q2B has grown, and they now have an entire series of conferences around the world. Well, QCE is right up there with them. And if you're interested in sort of the engineering side of things, as far as I'm concerned, it's the place to be. Oops, let's see. Why is some of this flashing around? So that's Hansi Muller who created it. This is Kathleen Kramer, who is the president of the IEEE, the whole shebang. The IEEE is like 400 or 470,000 engineers around the world are members of IEEE, and she's president of the whole thing, and she thought it was worth her while to show up in Albuquerque for this meeting. And then this is Hironori Washizaki, who is a professor at Waseda University, and he is currently the president of the IEEE Computer Society, which is one of the smaller societies that makes up the IEEE. So some of the things were held in this giant hall. That's where the keynotes were taken, but most of it, there were 18 parallel tracks going on at the same time. And so most of those were in rooms this size. This is us at the end of a workshop we actually organized on quantum network architectures in engineering. So that's Inder Monga, who's the head of ESNet in the United States, Joaquin Chung, who's at Argonne National Labs, and Shota Nagayama, who you'll see tomorrow, and some others. And of course, I got to have a little bit of fun, and I got this great Isotopes T-shirt at the minor league baseball game ballpark. So that was fun. So my recommendation is you should all submit papers to QCE, and we should all get together again next April. Sorry, next September. The deadline for papers will be around April 1. It hasn't been announced yet, I don't think. But the conference itself will be September 13th to 18th in Toronto. So David, if you're doing another one of these workshops, these summer schools next year, got to schedule around that. So I hope we'll all see each other there. All right, so quantum repeater networks is sort of the key direction we want to be heading over the next 10 days or so, I think. Roughly, quantum networks can be divided into 2 major categories. David, of course, can give you a much more fine-grained division of sort of what the capabilities of these networks actually are. But roughly, we can think of quantum key distribution networks and entangled networks. And the quantum key distribution networks are essentially a single purpose network. They create shared, secret, random, guaranteed secret classical data between end nodes for use in topics such as cryptography. Whereas entangled networks are a much broader class of networks, and they can cover many applications, one of which can be QKD. And in fact, the man who was standing right here an hour ago is one of the key people responsible for that, Arthur Eckert. I should have gotten a picture of him and stuck it up there, but I didn't. Anyway, the key ideas for both of these were developed in arguably as far back as the 1970s, but certainly in the 1980s. And the first commercial products for QKD were already available in the early 2000s, whereas with entangled networks, it's still not possible to actually get, go to the store and buy entangled networks. And that's because entangled networks are actually harder in a technological sense for a variety of reasons. So I actually did my own PhD on quantum computer architecture, finished my PhD in 2006. And then at that time we were going, wow, building quantum computers is going to be really hard. Maybe building networks will be easier. Let's work on networks for a while. And then after we worked on quantum repeater networks for a while, we went, you know what? Quantum repeater networks are as hard as quantum computers plus stuff, right? And so they're sort of inherently harder in some senses. But the first entangled networks are starting to appear, testbed networks, and we are pushing toward what we expect will be a commercial quantum internet sometime in the next decade. Any comments on that? Yeah. Good with that? All right. So the job of a quantum repeater, a node in a network, and by the way, I'm not actually wild about that term repeater because the term repeater has a lot of baggage, a lot of connotations in classical networks, but in this case, a quantum repeater is a very specific device, and it does 4 things. First, its main job is to make, well, hang on. Let's see. All right. Got these out of order, but we'll do this. So the job of the quantum repeater network is to make entanglement end to end so that end nodes can actually use that entanglement. And because quantum entanglement is a consumable resource, the job of the network is to make lots and lots of it. Okay. Not just a little bit. So then the job of the quantum repeater itself as a node is number 1, to create entanglement across a link, some fiber or free space link or something between 2 points. And then second, to couple entangled links along a path so that we can get end-to-end entanglement. Third, to monitor and manage errors in that, and purification or quantum error correction or both are the ways in which we're going to do this. And then finally, to participate in the management of the network itself, and that's something that tends to get sort of underplayed in its importance and difficulty, particularly when talking to experimental physicists. So there's a tremendous amount of work to be done there as well. So if that's a quantum network and a quantum repeater, then the job of a quantum internet is to do all of this across a heterogeneous set of networks, where those networks may be different physical technologies, they may be different logical technologies, such as whether or not quantum error correction is being used, and under separate management as well, and in an environment with minimal trust between those separate networks, which is effectively the way in which the modern classical internet itself actually works. So that means that, among other things, each of those networks has no knowledge of what the interior of other networks is. That's actually sort of a key point in the overall structure of things. And this also has to be done potentially in the presence of malicious nodes. So each one of these is a network, okay? And if I want to connect from here to someplace over there, then I have to create a path that crosses this entire set of networks and that gets end to end from one side of the planet to the other side of the planet. And all this needs to be done with everything else being essentially opaque to me. Okay. That's the distinction between a network and an internetwork. Each one of these, this is a network. It's got a set of nodes connected into it. It's one management domain. It probably has one set of addresses and other such concerns. And then globally, we connect a large set of networks together. Any questions about this? Yeah. So the question was, sounds like you're talking about first generation or even first and second generation of quantum repeaters. Would this also apply to third generation? And for those of you who don't know what the first and second and third generations of repeaters are, I'm not going to talk about that today. We're going to talk just about effectively first generation repeaters. But Bill Monroe is going to be talking about those second and third generation repeaters later in the week, right? What's that? Johannes Beauregard will also be talking about those multiple generations of networks. At this level of discussion, everything I've said so far applies equally well across all of the three generations of networks. But if most of you probably don't yet know what the first and second and third generation of networks are, but everything I'm talking about today, including entanglement swapping and purification and all that sort of stuff, that applies to what are called first generation repeater networks as defined by Wolfgang Duhr and Hans Briegel, who of course didn't use the term first generation networks. That term was created by Liang Zhang's research group some years later. Any other questions? All right, let's talk about networks. Just in general. Nice picture, huh? My picture. That's a network. Kinda, right? That's the Stockholm Telephone Exchange Tower from the late 1800s when telephones were just coming in. Basically, it's one wire connected from every one of 5,500 customers to a central office. And that central office connected you literally, when you picked up the phone, somebody at the central office picked up the other end of it and connected your phone to whoever you wanted to talk to, right? That's a network, right? We've advanced since then, right? Most of you, well, maybe not most of you, but many of you have probably heard of this network. This is the ARPANET, which is most commonly cited, including very commonly by Stephanie Vayner, who's the single most important who's the single most important person in quantum internet research these days, as the origin of the internet, the classical internet. And that's very true in an important way in terms of the continuity of the people involved and everything else. But the truth, of course, is that there was already a great deal of work going on networks, classical networks, well before the ARPANET was created. And the internet itself has incorporated many technologies from many other streams of development. And so it's not just one single line going from the ARPANET. But the ARPANET was created in 1969. It was originally 4 nodes. This is a map from May of 1973. Down here in the lower left is a USC ISI, which is the University of Southern California's Information Sciences Institute, where I worked for, how long did I work there? 9 years, I think, something like that, in a couple of different divisions. So ISI was one of the very early places on the internet. It was not, or ARPANET. It was not one of the original 4 nodes, but very soon after that. There was literally a copy of this map on a big piece of plotter paper, still on the wall at ISI when I arrived there in 1986, which was a little later. So we went from there. This is 1973. And at that point, the networking technology was still relatively primitive. In 1974 and 75, 2 guys named Vint Cerf and Bob Kahn created the modern internetworking structure that we depend on today. So this ARPANET was one network, basically. These guys figured out how to connect multiple networks together. Their protocol was called TCP/IP. They split it into these two layers, and it took the better part of a decade for the ARPANET and related networks to shift from the earlier protocol, which was called NCP, to the newer protocol called TCP. And on January 1, 1983, they just turned off NCP finally. So people I knew that at ISI back in those days still had these little buttons like pinned to their board or something. That brings us to, this is a map of the internet from 1989. You'll have trouble finding a map of the internet any newer than that because people have basically, there's almost no way to sort of represent the modern internet in any sort of graphical construction. Okay. That brings us to Steve Deering's OIST. This image is from a set of slides that a guy named Steve Deering, who at the time worked for Cisco, presented at an IETF meeting in London in 2001. And he was at that time concerned about the proliferation of protocols, was particularly what he was talking about. But the concept has far outlived that particular concern. And the notion here is that IP, or the internet protocol, is the common language that all of the nodes on the internet must speak. But beneath that, you have a lot of different choices of other kinds of networks and different kind of physical connection that you can use. And then above that, there are a variety of other types of protocols and then a variety of applications. And that's one of the key things about this entire structure. And I'll ask you about this guy later, who's not Steve Deering. So this brings us to this modern architecture, more or less. Commonly, you will hear about a thing called the OSI model, the OSI 7-layer model. How many of you all have heard of it? Only about half, okay, or even less than half. The OSI model is often called the 7-layer model for a network architecture. And it ranges from the physical layer down here, where you're talking about voltages and timings and how quickly signals are allowed to change and things like that, through the data link layer, which is how do you package something into one message on the network. And then ultimately, or well, not ultimately, the network layer on top of that, which gets you across multiple hops in a network. And then the transport layer, which builds a connection end-to-end, or whatever structure you actually need for that end-to-end communication. And then you've got the session layer and the presentation layer that we don't talk about a lot, in the application layer on top. Well, this is the original OSI model as defined, I think, in the early 1980s. TCP/IP actually has a slightly different structure. It essentially has 4 layers: the network access layer, the internet layer, the transport layer, and the application layer. But on top of this, there are a whole bunch of applications: HTTP for web browsing, SMTP for email, FTP for file transfer, the domain name service, other sorts of things. 2 main transport protocols, TCP and UDP, with an important modern variant of UDP called QUIC, which we're not going to talk about. Then you've got the IP layer here, and then a set of possible different network layers underneath. Questions about this structure? This is one of the key concepts in all of networking in modern architectural terms. And it's been around for about 4 decades, give or take. Questions on this structure? Everybody's good with this? All right. This is what a packet on the internet looks like, give or take. The diagram at the top is the Ethernet header. Then the part that's in orange here is the IP header, and then the part after that is the TCP header. So every packet that's getting sent, between this laptop and any place, or your phone or any place, it has a series of headers attached in front of the actual data that you're dealing with. So the TCP header deals with making sure the packets arrive in the right order and that nothing's gotten lost, checking for the integrity of the data. The IP layer is responsible for getting it from place to place across the entire internet. And then the Ethernet header is responsible for that first hop, getting it from where the packet originates to the next gateway. Each of those headers has a size, and some of these are slightly variable in size, but they, give or take, these are roughly right. So all of this is put in here, and then after that, there's some data chunk that ranges from a few bytes up to a few thousand bytes or something, give or take. That's the modern structure of how packet-oriented communication gets done in the internet today. So let me talk about a set of networking design issues or questions. First off, the basic communication model. You saw that Swedish telephone tower, and now we're talking about the internet, right? That early Swedish tower was circuit switching. Literally, when the operator connected two phones together, it meant you had a physical electrical connection from end to end across the network. That's not the way we do things today. Today we deal in terms of datagrams, where a long set of digital data gets split into pieces, and each one of those pieces gets sent and controlled more or less separately, although there are a lot of complications in the modern internet. So typical sizes for those packets across Ethernet are 1,500 bytes. Across other types of networks, 576 bytes. That's pretty small by today's standards when you're talking about transferring hundreds of megabytes or gigabytes worth of data, right? So Farber Sensei is fond of saying, paraphrasing a bit, that the principles of these constructions basically remain the same, but because the technology, the business environment, the economic environment, and the political environment all change, it's worth revisiting every once in a while. And at the age of 91, he is musing, maybe we should be going back toward circuit switching networks, or at least raise the size of the minimum transmission unit or maximum transmission unit by orders of magnitude to on the orders of megabytes instead of kilobytes. Right? So there's still actually a lot that can be done. We are not at the end point of the evolution of network technology by any means. Right, so multiplexing, like I said earlier, there are different definitions of this. When I'm talking about it, I'm talking about wanting to share the use of one link across the network, where each one of these colors represents a separate end-to-end application connection. So A is talking to K, B is talking to L, C is talking to I, D is talking to H. So each of those, where we have multiple lines here, we have multiple conversations that are sharing that particular link. So when I say multiplexing, this is usually what I mean. But there are different ways in which you can actually multiplex things. One that I think sort of gets undersold is spatial reuse. And if you read histories of the mobile phone network, you'll actually see some good discussion of that, because the realization that you could have small cells in a cellular phone network was actually a very big one that provided a lot of our modern capabilities. Temporal multiplexing, people usually talk about time division multiplexing, or TDM, which means I get 1 millisecond, you get the next millisecond, I get the next millisecond, you get the next one. We're alternating or moving from one to the other. But this basic datagram approach that we've been talking about is what's called statistical multiplexing. It's just sort of the assumption that over time there are going to be random behavior of the different connections, and we can reuse the resources relatively opportunistically, and that it's all kind of going to work out. That has a lot of implications, and we could talk for days and days about the implication of whether or not that's actually good and whether or not it's going to work. And again, that's the kind of thing that Farber Sensei is worried about. We can also talk about wave division multiplexing, where we put multiple communication sessions into the same physical path, like the same fiber, but on different wavelengths. And recently there's been a series of experiments, which I don't have slides on, where people have multiplexed quantum signals together with classical signals in the same fiber. And that's a tremendous accomplishment. But the work that's been done so far, for example, has been putting the classical stuff on C band and the quantum stuff on O band, meaning they're separated by huge differences in the wavelength, because the classical signal is very, very strong, and it will swamp the quantum signal under any reasonable circumstances. And then there's CDMA, code division multiple access, which is one form of multiplexing there as well. And so there are different ways in which we can share these resources in order to accomplish this goal of having multiple communication sessions running across the network all at the same time. Questions or comments on this, multiplexing? Yeah. Makes sense. Like usually the one that different degrees of freedom that I've seen papers that talks about using different degrees of freedom. Using different degrees of freedom of yeah. Yeah, so that's actually a good way of putting this. Each of these is a separate degree of freedom of your communication session. And as long as you can distinguish your communication session using at least one of these important degrees of freedom, you can do this. You can put multiple sessions into the same place on if there are n axes of things you can distinguish, then you can put different communication sessions on the same set of n-1, and then just use the nth one to distinguish the set of communication sessions. So yeah, you can do this with any of the degrees of freedom in essence, or you can gang them all together in order to actually aggregate the bandwidth to create one massive session if you want to do that. And there's also a lot of interesting work on supercomputing systems that actually does things like that. Yeah.
I didn't quite catch what kind of multiplexing is the one that you use?
What kind of multiplexing is which?
The one that you're talking about.
Well, so what's the best one for the quantum internet is an open question. That's still an important area of research. This particular paper actually is one we did all the way back in 2011. Yeah, just a second. And this one was, as far as I am aware, the first simulation and analysis of a quantum repeater network as opposed to just a chain of quantum repeaters. And in that analysis, we used essentially a form of statistical multiplexing. We also used buffer space multiplexing, meaning we divided out the available memories into different connections and investigated it. And we found some interesting conclusions that seem to show that statistical multiplexing, like the internet does, actually probably works okay for quantum repeater networks. But that depends on a certain set of assumptions, and I think it's time, in fact, to revisit that set of assumptions. And in fact, Luciano Aparicio, who did that work back then for his master's degree, today is having his entrance ceremony to Keio. He's coming back for a PhD. And so I don't know if we're going to follow up directly on that work or do other work with him for his PhD, but the man is back as far as I'm concerned. Yeah, you had something else?
Circling back to my question, how does that get realized, like in terms of engineering, when you have different degree, like a multiplexing and mix all together?
So how does it work if the okay, that's why I'm mostly repeating the questions, but yeah, we can use the mic. How does it work in practice? So spatial reuse, and a different form of spatial reuse just might be a set of parallel fibers, right? And you can aggregate those together, or you can run separate conversations over it. And just mathematically, if you do the full mathematical representation of this, you get a complex signal that's the aggregate of all of these degrees of freedom, and then you can sort it out using mathematics and finding where the orthogonal signals and all of this are. It's an interesting topic. And yeah, there are actually still even other characteristics I didn't list up here that we could do. Let me go on in the interest of time. Let's see. So naming is another one of the very big deals in in a network, naming and addressing. This is John Postel, who was also at USC-ISI. I worked for John for a while. Excuse me, pointing at a map of the early internet, and John was the IANA, the Internet Assigned Names and Numbers Authority, which is now a large organization, but in the beginning was just John, and he just kept it in files on his workstation. But a name, there are many different kinds of names, many different kinds of names, and there are people who invest their careers in theoretical computer science in naming, but fundamentally, we can talk about a name being either an identifier or a locator. And an identifier is just your name, right? It's I'm Rod Van Meter. The locator is, well, I am in the Seaside campus building at OIST right now, right? So the locator can be used to help find where you are, whereas the name is, whereas the identifier is intended to uniquely identify you. And there are cases where you are, one of the important things about a name is the context in which that name can be resolved and the context in which it can be considered unique. So, I'm the only Rod in this room, right? So you can just call me Rod, and it's completely unique, it identifies me uniquely here in the room, right? But if we go to some larger area, there are going to be many other Rods or Rodneys out there, and so it will become less unique, and then it becomes important to continue to distinguish in another fashion. One of the important aspects of naming in the modern internet is actually a system called the domain name system, which translates one type of name to another type of name. And the normal use of this system is through a hierarchical structure called the domain name structure or the domain name system. And it translates a human readable text string into a numeric IP address that can be used to actually connect to somebody. So loosely, but only loosely, that domain name serves as the identifier, and then the IP address serves as the locator in this context. And by the way, if you value your money, do not play poker with this man. Let's see. So, routing. This is actually this picture actually is taken from a paper we did about 15 years ago now. Well, 2013 was when it was finally published. But if you've got a topologically complex network, you need to figure out how to get from one place to another on the network. Right? So if the good links here are marked with circles and the fair links are marked with triangles and the poor links are marked with X, which route's faster? Figuring that out is the job of the routing system and the routing protocol. I asked how many of you all are familiar with Dijkstra's algorithm, and actually, to me, this was one of the most surprising things, and it's one of the reasons I'm putting in a lot of this stuff, was almost nobody said they knew Dijkstra's algorithm. So we're going to talk about Dijkstra's algorithm for a few minutes. This is Edsger Dijkstra. Dijkstra's algorithm, which he published in 1959, is just a graph theory problem, and it's finding the shortest path or least cost path on a graph. It's interesting because it's solvable in polynomial time. It does not take some exponential time to actually solve on the graph. And ultimately, the outcome of this is what you do is you build a spanning tree from some root on the network, okay? This is an animation. Is the animation running? Yes, the animation is running, taken straight from Wikipedia. And the interesting thing about this is that it can be used not only in one place, but it can be used in a distributed fashion. It can be used in different places to do this. Now, this is an example here. Let's see. Let me see if I can do this. We've got the nodes 1, 2, 3, 4, 5, and 6, and each one of those links has a cost associated with it. So the cost associated with the link 1 to 2 is 7, 1 to 3 is 9, 1 to 6 is 14, 2 to 3 is 10, and 6 to 3 is 2, and then this one is 9, and this one is 11, and this one is 15, and this one is 6, okay? The animation that's shown here is working from node 1 out. Right? And what it's going to find is it's going to build a spanning tree. Let me see if I can do this separately over here. 1, 2, 3, 4, 5, and 6 again. Excuse me. And the spanning tree is it's actually going to build the shortest connection to 2 is just that direct connection, and the cost for that is 7. Now, to get to 3, you could go either this way, which has a cost of 10, or that way, which has a cost of only 9. So it turns out to be 9. To get from 1 to 6, well, 6 is directly connected, but the cost for doing that is 14. So that's pretty high. And in fact, there's a shorter route via node 3. And so we'll actually use this. Oh, let's see. Excuse me. My apologies for those of you on the recording. So the cost to get to 3 winds up being 9, and the cost to get to 6 winds up being 11 in the eventual spanning tree that's developed. And let's see, the cost to 4 winds up being, yeah, right there, 22 winds up being 20 actually is the best route to here. And so you wind up with this. And then the best route to node 5 winds up being also 20. Let's see, so what's the route via 20? So this is 5 and 6. Let's see, so this was 20, right? What? 6 to 5 this way. And so the cost for each of these wound up being 9 plus, so that was 2, 9 plus 2. So I don't remember what the final cost of this was. Final cost of this was also 20. So you've built what's called a spanning tree here, right? Now the interesting thing about this, we did this working from node 1, right? If we did the same thing working from node 4 instead, and 4 wants to get to 2, I'm just going to do this very sort of ad hoc. It will wind up generating a set of different paths. It will build a different spanning tree using different links. And I haven't actually calculated this, so the green one may actually be wrong. But that set of spanning trees will be consistent. So node 1, if it knows what the set of links and the set of costs in the network is, and node 2 or 4, if they know what the set of links and the set of costs is, they can independently calculate their own spanning trees. And the number one thing about that is you're not going to end up with any routing loops. You'll never wind up with the case where somebody says, my best path to get to Joshua is to hand it to David. And then David says, my best path to get it to Joshua is to hand it to Rod. And so we just keep handing this message back and forth. Right? That would be a routing loop. But Dijkstra's algorithm calculated in this distributed fashion actually winds up being, I started to say internally consistent, but it's across this distributed system, and so it's just not, it's globally consistent, not just internally consistent. That's one of the key properties of this. And all of that is contained in this. This is Dijkstra's entire 1959 paper. Less than 3 pages. It's 2 pages of text, right? Holy cow. This is one of the most important discoveries of the 20th century, and it's 2 pages long, okay? Holy cow. But we use it today in the internet all the time. There are 2 major network routing protocols that depend on Dijkstra's algorithm, one of which is called OSPF, the open shortest path first version of this. And the specification for OSPF is 244 pages in its 1998 form, and it's been updated again and again and again by a set of different protocol extensions. So getting from that 2-page idea to something that works in a robust fashion in today's modern internet, where all of the T's are dotted and the I's are crossed, or whatever, that's a tremendous amount of work, and that's where all of the network and protocol engineering comes in. Excuse me again. And that takes us to this internet, right? Takes us to where we want to be. And that brings us back to this, right? This picture, which I showed you a little while ago, every single, you can't even really see them, but every single little dot on this, that's not a node. Every single one of those dots is a network. So this whole thing, there were probably, I don't know, 100 million nodes or something on the network back then. There are tens of billions now. Oh man, excuse me. In internet routing, basically we talk in terms of an interior gateway protocol versus an exterior gateway protocol. And that interior protocol is what's in here. Inside of this, to get from here to here, you can use anything you want to use. You can use carrier pigeon, you can just design it all statically, you can do anything you want to do. But to connect the set of networks together, we need one shared mechanism. And that shared mechanism is a protocol known as BGP. You can, by the way, actually, although I didn't write it up here, you can in fact use BGP as your IGP, so you can run just one protocol if you want, although the operation is actually fairly different. And also the local area networks interiorly have their own routing protocol, and the most common of those in switched Ethernet is a thing called the spanning tree protocol, which is not actually directly related to Dijkstra's algorithm. And it was developed by a woman named Rodney. But this is all sort of the basic ideal, and then there are all these complications of VPNs and tunnels and overlay networks and yada, yada, yada. It gets really complicated. Questions? Routing. Yes. Let's do the mic thing, make Yukari-san happy. You send that back to him. You may have to turn it on. I didn't check if it's on.
Yeah. There you go. On the map of the internet, what does the colors refer to?
Sorry, say that again?
What does the color refer to?
What does the color refer to on this giant picture here? The color here referred to separate backbone networks. So the green network is one network, and then this red network is another one of the backbone networks that's connecting a set of networks together. So one of the things that has happened over the evolution of the network over the last 30 years is it has gone from really being this diagram like this with all of these smaller networks to almost a hierarchical structure where people go from essentially a leaf in the tree toward the root, and those roots are the big global backbone networks. And so this is actually a fairly early stage of the development of those major backbone networks. And today, globally, there are maybe 8 or 10 of these major backbone providers, and they're called the hypergiants. And so the economies of scale have actually consolidated some of this structure just in terms of business sense. Yeah, question. Sorry, say that again.
You mean tier 1 networks?
Yes, so another term for this is tier 1 networks. Yeah, I've got a question over here. Means we gotta have the mic all the way over here. Is this on?
I was just wondering, how do you, like in real life, how do you determine these numbers that connect each nodes, like the 14.9 to 10.11? Like, do you have an idea how people actually do to determine those numbers? Or make
Okay, that's a good question. So I have actually forgotten to tell you all that. Dijkstra's algorithm originally is defined as purely a graph theory algorithm. Man, excuse me, I really have a cough today. So Dijkstra's algorithm was defined with these being just unitless numbers. And in fact, the OSPF itself, where did I put that? OSPF, those costs are still defined as unitless numbers, dimensionless numbers. They're just a number. And they're defined by management level agreement or physical configuration between these two nodes. And yes, these two nodes both have to agree that the cost of this link is 14. But in practice today, a common approach to setting those numbers is inverse bandwidth, actually. And if I remember right, man, I haven't looked at that in a while. I'd have to look. If I remember right, a link cost of 1 in OSPF means 10 megabits per second. And so a link that is 1 gigabit per second then would be assigned a link cost of 0.01. And you can do whatever you want, but that's considered sort of a common standard practice. As long as people agree on what the cost of the individual links is, you're fine. Yeah, question in the back. And I'm going to cut this off in a couple of minutes, or we're not going to get through the QCE stuff I want to talk about before lunch.
How many layers of switching does, say if you send an email or something, maybe it will go to some local network, and then how many layers will it get to, they say, like the transatlantic fiber optic cable, that sort of thing?
Are you talking about how many protocol layers or how many hops from here to there?
Either or both.
So the number of protocol layers, you've got, sort of the email layer, which is SMTP, maybe some security stuff. Then you've got the transport and control protocol, that's TCP. Then you've got IP, then you've got Ethernet, and the physical layer on down. And you'll see a lot of diagrams where it's drawn as the equivalent layers on separate nodes communicate with each other. And that's a logical thing because the message actually passes from place to place. In terms of the diameter of the network, I think 12 to 14 hops is roughly the diameter of the global network. I could be wrong on that, I'd have to check. So one of these one of the things I pointed to here is from the blog of a guy named Jeff Houston, who provides a lot of really excellent sort of description of the modern behavior of the internet. Excuse me. And the modern internet consists of, well, each one of these networks is called an AS. It's called an autonomous system. And how many autonomous systems are there in the world right now? I should know the number of this off the top of my head, but it's on Jeff's blog somewhere. How many autonomous systems on the internet? Let's see. Wikipedia page. I was looking for Jeff's blog because I know he's got that, but I didn't see it there. But let's see. By December 2020, the number of allocated ASNs, autonomous system numbers, exceeded 100,000. As of 2025, there are roughly 120,000 allocated systems. So that means that the internetwork is a network of 120,000 separate networks. But you know, they're estimated to be on the order of 10 to 30 billion devices connected to the internet. So that means, you know, we're at 100,000 or more devices per network. So you got 100,000 networks of 100,000 devices each. Did I do the arithmetic right there? Give or take. That's a lot. Look for Jeff Houston's blog on this. He always has excellent data on this. And I'll see if I can find it for you later over lunch or something. All right, let me speed through these last little bit here so that we can do the QCE stuff before lunch. Let's see, we covered that. If you want to learn a little bit more about the physical layer on optical stuff, I was talking to my students back in the spring about this stuff, and I wound up putting together a couple of blog postings on this, which you can reach from the slides. From the older SDH, the synchronous digital hierarchy, which was defined in the US and Europe, to more modern day stuff, including connections to the optical Ethernet. You can learn quite a bit from there, and it will also point you to some of the standards. All right, so back to quantum networks just briefly. There are going to be many different kinds of nodes on a quantum network. There's not just one thing called a repeater and we're done. There are going to be a set of different types of end nodes. There are going to be sensors and measurement nodes and computational nodes. That's supposed to say storage, not measurement. I think there may actually be one more missing from this anyway. Generations of repeaters, 1G, 2G repeaters, a router, which in our terminology, a repeater has exactly two interfaces, one that goes to the left and one that goes to the right, whereas a router has 3 or more interfaces and may also serve as the boundary between separate networks. Supporting nodes like optical switches and entangled photon pair sources. And our lingo, EBPS, is an entangled photon pair source, just a sec. Bell state analyzers, and then a couple of things on the advanced topics of graph states. All right, we got a question over here. Where'd the mic go? On the, let's see. So this set of icons, by the way, are free. Anybody can use these. We encourage people to use them because it will help improve communications, we think. Yes, question?
Okay, so where does quantum switches fit into this diagram?
Where does what?
Quantum switches.
So actually, I know you're from Delft, right? The Delft people have talk about quantum switches in a way that's a little bit different from our terminology. I think they include memory inside a switch. And in our lingo, this optical switch has no memory. It's just a thing that switches photons from place to place. I believe the definition of switch is closer to what we consider to be a router.
Those are two different types of switches, right? One is distribution switch where you have memories. The other one is entanglement generation switch. So it depends on, yeah, thank you.
All right, I recommend reading this. There are actually two versions of this. There's one with my name on it and one without my name on it. So you all should definitely read the version with my name on it, right? This is a report that was done for the US government some years ago, and then a year or two after that, a very similar paper appeared in PRX Quantum by mostly the same authors. But in this, we looked at, and this is a chart that I created for this report, different types of networks and the different types of nodes. And this is very qualitative, but let's see. So MI is machine interconnect, DCN is data center network, local area network, mobile network, metropolitan area network, wide area network, satellite network. And then R and C just indicates whether or not those types of nodes we think will be rare or common in that particular kind of network deployment. And this can kind of be used as a rough guide to development. If you are focusing on building data center networks, then these are the kinds of nodes that you should be concentrating on. You should be concentrating maybe on a router and on a Bell state analyzer, and of course the computational end nodes, and the optical switches, right? Whereas in other cases it may be different. So this is just a very qualitative sort of thing, but that's part of this roadmap on interconnects. All right, there are some additional references. Each of these are live links in those, and most of them go to other slide sets of mine covering work over the last many years. Some of these go to various places. We have a particular vision of the quantum internet in what we have put together, covering sort of the whole stack. And I think the single best description of that entire quantum internet architecture is actually the PhD thesis of this guy, Napan Benchasattabun, who just on Friday received his PhD, and that's his thesis. It's available on our group's website. He hasn't been able to get it to compile properly on the archive yet, and so it's not on the archive yet because he's using some packages that archive doesn't like or something, right? But it builds on a lot of the work we've done, and it's really a brilliant description of this. Of course, some of it's very specific to the specific research topics he's talking on, but chapters, 2 through 4 or something in his thesis, I think are a brilliant description of our view of the quantum internet architecture. All right, and I think that's pretty much it. Boy, you guys are lucky to be spending 10 days here, and I'm sorry I'm gonna be going home. That was last night, right there. Let's see, any questions on this material before I go on to essentially the second half? And we're now down to just 52 minutes. But this conversation, I think, is important. I think this is setting a good basis here. And by the way, not only that particular set of links, but I'm gonna have more links and references for you all in the more coming sorts of things. I'm gonna throw dozens and dozens and dozens of references at you, so you'll have your readings set out for the next 18 months or something, right? Yeah, question?
So you talked about a lot of classical protocols for the internet. How these will be modified for the quantum internet? Because the physical layers now change and the constraints on these are somewhat similar, but somewhat also different as well. So like now I know that TCP/IP protocol, the new version 1.3 has post-quantum ability. So how for the quantum internet it will be different?
That's an excellent question. So how are we going to go about adapting all of what we know, what we have learned about network architecture over the last 60 years into the quantum world? And that's actually the #1 engineering approach we are taking in my group. Is we are working to bring what's known about classical networks into the quantum world. And so for one example, in the routing protocol, going back to his question about the link cost that we were talking about earlier, that research that one of those papers that I pointed to from 2013 or something, we investigated what a good link cost might be that's equivalent to this inverse bandwidth that I was talking about that people often configure OSPF with. And we found that saying the inverse rate of bell pair generation at a particular fidelity, so incorporating purification into that, which we'll talk about a little bit more later. Incorporating purification, getting to a bell pair of a particular fidelity across the link, what's the rate at which you can do that, seems to make a pretty good metric for this. And it doesn't mean that then when you combine the path, that you're going to get exactly the performance that you might project out of that, because paths behave in a much more complex fashion in the quantum network than they do in the classical world. But we think it's good enough. We think that ranking is going to be we compared the performance of an entire path as simulated versus ranking those compared to how that routing protocol would rank them, and the rankings are pretty much equivalent, and so we think it's going to serve actually pretty well, because with OSPF, right, you're just doing an abstract number, and that doesn't have a very direct relationship to your performance there anyway. Is this quick?
Yeah, it's a comment.
Okay.
Hello?
Yeah.
Right. So maybe on the link cost, I have a comment on Dijkstra. Maybe mention that it doesn't work on negative weights.
Yeah, go ahead. I'm listening. I'm just getting more tea.
So Dijkstra algorithm doesn't work on negative weights, and maybe it's important to point that out.
Yeah. It's actually a little bit outside my wheelhouse, but I think people have actually investigated what happens when you do set negative weights on networks, but that's sort of a corner case. People work in terms of real numbers, real non-negative numbers. Right. All right, let me go on, or we're going to run out of time before lunch, and I want to get us to lunch on time. Let's see. Here we are. I will get to skip through some of this stuff that we haven't already done. So the link to this is in that first set of slides from if you didn't get it yet. So quantum multi-computers, and this is roughly going to be a discussion of data center networks as opposed to wide area networks. This, by the way, is our campus, which is kind of nice. QCE, which I mentioned, was actually on the news while we were in Albuquerque pretty frequently, and Albuquerque really went out of their way to make a great week for us. I did a dedication of this to the people who couldn't get to the US, so I know some people in particular from Europe didn't want to go because of the current political situation in the United States. But I think it's worth remembering we're in sort of an extraordinary era here with quantum information and AI, both for better or worse, and things like mRNA vaccines and the fabulous work that's going on cosmology and astronomy with the introduction of new instruments, but also climate change and COVID-19, and there are 6 active wars around the world that are killing more than 10,000 people a year. Right? And there are many more conflicts actually still going on. And also, the assault on science and higher education and public health in the United States, which has gotten even worse in the 2 weeks since I created this slide. It's just astounding what's going on. But the IEEE's logo, or motto, not logo, motto is advancing technology for humanity. And so I think it's really absolutely crucial to remember why we're doing this. When I was your all's age, I was a pretty pure technologist and thought, well, we build technology, technology automatically makes the world better, right? Well, that's not the case. It depends on how that technology is actually applied. And so it's incumbent on all of us to consider how what we are doing actually affects everything else that's going on in the world. So just a comment. So let's talk about these networks for modular systems. And I'm going to skip over some of the stuff as we go. because we covered a little bit of it earlier, and also some of it Shota's going to talk about tomorrow. So I'll give sort of a skim over some things that you'll hear in more depth tomorrow. But this, I'm sorry Bill and Kai aren't actually here. This is the first quantum conference I actually went to, which was in Kyoto in 2003. Yeah, that's me. I was substantially skinnier then on the, this was already a mid-career shift for me. I had worked on computer architecture and operating systems and network storage systems and things like that. But this was the EQIS conference, which was the predecessor to what's now called the AQIS conference series, which migrates around the world and currently is usually held in August. Where was the last one? I don't remember. It was last month was somewhere. So this was everybody at the conference, right? I just told you all that 1,700 people were in Albuquerque. This was everybody at this conference in 2003. That's me. And since then, I have collaborated with Bill Monroe, whose voice you heard last night, and Kaya Nemoto's, whose voice you probably didn't hear very much of last night. If we could average the voice volume between the two of those, we'd be in great shape. And then Francois Laval and Yoshi Yamamoto, so those are people I've collaborated with since then. But my thesis was back in 2006, and I think I was one of the first people with a formal background in computer architecture to actually work on quantum computers. So this is a diagram from my thesis back then, which is available on the archive if you want it. And then this is the group that I lead today. And this isn't even everybody. This is only about 2/3 of us. There are a total of about 37 or 38 of us. Let's see. Soon is there. Mia, you weren't here this day? I guess not. The day we took that photo. This was last fall. And this is where our collaborators and members come from. And even this, I've noticed a couple of mistakes. I've forgotten a couple of countries out of it. The dark blue is current or recent Aqua members. The red is current collaborators, where they are from. And the lighter color is other places they've been. So this is a global effort. It's not something that one company or one country can do. I actually haven't counted how many countries do we have represented here in the room? A dozen more, right? So this is a global effort, and we shouldn't be cutting anybody out of the overall process. But in the process, I have been privileged to write papers with at least 110 different authors, and none of these are major, these huge collaborations. Those are all small collaborations, which led me to have a bunch of titles, which you all don't care about, and. As I said earlier, we are working to get from experiment to systems. The question is, what takes us in that direction? We want to get from this to this. This is one of the largest and fastest supercomputers in the world. This is a machine called El Capitan at Lawrence Livermore National Laboratory in California. Right. And this we already talked about, so we'll skip that part, except that there's Charlie Bennett and Charlie Bennett again, and then Wolfgang Duhr. So Charlie's responsible for both teleportation down here and QKD up there, and then that's Wolfgang Duhr, whose work led to the what we now call 1G quantum repeaters, right? But mostly what we're going to talk about is multi-computer and data center networks for the next 45 minutes or so. Entanglement, I think I can actually probably mostly skim over this for this particular audience, but the idea is that nodes emit photons which meet in the middle, and this particular structure we call MIM, or memory interference memory. The device they meet at in the middle is a thing called the Bell State Analyzer. Right? So some of you may be more theoretical, and so you may be a little less aware of how the entanglement that you're writing theory papers about actually gets generated. This is one common structure for how it gets done. Not the only by any means, but one common structure. You need a set of things between for those photons in order to actually enable what's called entanglement swapping, which is directly related to teleportation. And fundamentally, those photons need to be indistinguishable. We were talking a little bit about degrees of freedom earlier. Well, there are a set of degrees of freedom for an individual photon. And you need for those two photons that arrive at that Bell state analyzer to be essentially completely indistinguishable. One area in particular is that you need for these wave packets to actually overlap in space and time. They need to arrive at the same time and place. The first element they'll hit in a Bell state analyzer is a beam splitter. And if one photon is early and one photon is late, then this will give you poor visibility, which results in poor or no entanglement. So we use a device called an optical delay line, which is essentially a movable set of mirrors, to lengthen or shorten the path that one of those photons is actually crossing, and allows us to adjust the time to get the two photons to arrive at the same time and same place. And that results in what's called the Hong-O-Mandel dip when this all works properly. This is data from our lab. These are individual photons created via spontaneous parametric down conversion, SPDC. If you're out here, basically what happens is the two photons are arriving at the beam splitter at different times. You'll see in the animation there, they're getting there, and then they exit independently. Sometimes they exit out the same port of the beam splitter, sometimes they exit out of different ports of the beam splitter. And so that gives you data like this, where the vertical axis is the number of times the two detectors clicked within a particular time interval. Then the horizontal axis of this is the adjustment of the position of the mirrors in that optical delay line, resulting in changing the path length. And when you do that well, you get this so that the two photons arrive at the same time, and then they wind up exiting the same port of the beam splitter with what should be unit probability. And so then this two detector coincidence in a perfect experiment, this dip here will decline to 0 when you get the two wave packets to actually line up perfectly. That's the fundamental thing that's going on right here. Now this is essentially a calibration test, or how you adjust your system to get this and to get the photons actually in the right place at the right time. But the way you actually structure this into an overall link is that you begin with each one of these photons entangled with a memory. So this photon's entangled with a memory here. This photon's entangled with a memory there. And after the Bell state analysis, what happens is that you have entanglement memory to memory. And this is what we call in our lingo an MIM, memory interference memory link. Any questions on this structure? This is sort of a common link structure. There are quite a number of experiments worldwide in different technologies done on this. How many of you all have worked on things like this? A handful. How many of you have been in a lab and seen things like this? A few more, right? Good. All right. Now, what do we use it for? We're already basically familiar with the key idea of teleportation, I think, meaning teleportation moves data from one place to another. But one of the other structures, one of the other things you can do with this is you can actually use it to execute logical or execute operations between qubits that are held in different places. So we have here a circuit with 4 qubits in it, the upper 2 of which are held in node 1 and the lower 2 of which are held in node 2. And over here, this squiggly line, this is where we have that bell pair, where we have that entanglement connected between the 2 of them. Now what happens on this, each of the nodes, node 1 and node 2, execute CNOT gates locally between a qubit they hold and that qubit that comes from the bell pair. Then there are a pair of measurements, one of which is a Z measurement and one of which is X measurement, and some classical communication. And this overall structure turns out to be equivalent to a CNOT gate between this qubit A and qubit B, with those 2 qubits held in physically distant nodes with that CNOT operation mediated by this belt pair. There was an earlier paper than this written by Ike Chuang with a more complicated structure, but then Jens Eisert in the year 2000 and a set of collaborators defined this structure, which is very simple and very straightforward and builds on key ideas of teleportation. Questions on this? This one's a really fundamental idea. All right. So let's take that's sort of the foundation, right? Let's take a look at my view of the where we need to go as a community on this overall system structure. The early qubits were built all the way back in the 1990s, right? But just a handful of experiments. And in time-honored fashion, we want to get from the lower left corner here to the upper right corner of a plot, where the horizontal axis means we're going to have more application qubits available, and the vertical axis is higher fidelity, right? So, a few years ago, John Preskill gave us the term NISQ, noisy intermediate scale quantum systems. And then today we are essentially at the era of the earliest fault-tolerant demonstrations. And so companies like Quera and Google and others have been showing that, yes, indeed, quantum error correction works, and you can get a lower residual error rate, a lower effective rate after executing error correction than you had with the start of the original physical belt pairs. Or physical qubits. Now, where we're going from there is we're going to increase the code distances that people actually use in the error correcting. We're going to improve the fault tolerant systems overall, and we'll get to a limit that I call max SQ, which is the maximum single node or single chip quantum device. How many physical qubits you can get into one chip or one ion trap or one NV diamond device or whatever your technology is. There is some upper limit to that. Right? Once you get to that limit, where are you going to go? Well, Spinal Tap, you got to turn it up to 11, right? Well, we need to add interconnects to this, and that will ultimately take us to what we call a fault-tolerant quantum multi-computer. Okay. That's where we got to go. As far as I'm concerned, this is pretty much non-negotiable, right? We've been talking to various people and from different companies, and you might talk to companies and say, well, we can build one device that'll hold a few hundred logical qubits. We think that's going to be good enough. ... And to which my response is, what you need to be thinking about is not what's the smallest quantum computer that's useful, but what's the biggest quantum computer I might ever need? And there's always going to be some advance to this that means that you're going to need more qubits to the system. We're going to have more applications and more things in this. So ultimately, you have to find a way to interconnect those smaller set of systems into larger structures. From my point of view, that's pretty much a given. So, in terms of the history, now this is really convenient history part, I think, since we're in a school here, right, a summer school. This idea of connecting multiple computers together to solve one problem together, it's pretty obvious, right? It's not something that required the world's most incredible insight. But nevertheless, getting from that basic idea to realizable systems is a lot of work. The earliest place that I know of that this was written down was in a paper by Jungsang Kim and company, shortly after Jungsang moved from Bell Labs to Duke University. Jungsang was a student of Yoshi Yamamoto's at Stanford, but then went to Bell Labs and then from there to Duke. He and some others proposed putting multiple ion traps in a room and then connecting them via some sort of optical interconnect at the time. They proposed a particular physical structure with multiple logical qubits per node and then a complete crossbar that would interconnect all of the nodes together in this system. Well, that paper of Jung Science was 2005, but it had been, oh, and by the way, my apologies if somebody is working on this and I don't have yours on this slide or your favorite work, whatnot. But at about the same time, I was working on from the top down, trying to figure out what kinds of systems we would need to build. And Daniel Loy, Simon Devitt, and Austin Fowler in Australia were working on similar structures. And Liang Zhang and the group of Misha Lukin at Harvard was where he and Jake Taylor and others were working on this. So the three groups of us, we published papers in the 2006-2007 timeframe on this. And I was trying to figure out what the requirements of the system are, because I'm an engineer. You got to start from something, right? If you don't know why you're building a system and what it's going to do, you have no idea how to evaluate if it's a worthwhile system or not, right? So I was working for the top down, and these guys were working on a different approach to interconnecting ion traps, and Liang was working on a different approach there. Then in the 2010 to 2015 timeframe, I worked with Thaddeus Ladd and Austin Fowler and Yoshi Yamamoto to build a massive system, or propose a massive system. And this would have been 6 billion quantum dots and something like 16 million laser ports. And it would have been sufficient for running Shor's algorithm at some particular scale. And arguably, I think this caused Yoshi and maybe other people to actually change direction in their research, because we proposed this and Yoshi's like, well, that's not going to happen before I retire, right? So I'm going to go do something else, right? But it was always only a baseline, and any of these architectures depend a great deal on what you assume about the effective yield of your devices and what the physical gate error rates are, and a lot of different things. And we were looking for how big would a system actually be if you just barely got to better than threshold. You just barely got to the point where error correction really kind of works. And so I think we were like a factor of 3 below threshold or something in this analysis. And also we assumed in this structure, for what I still believe is the first time in the world, and very few people have followed up on it, what do you do when the yield of your devices is less than 100%? So you make a chip and not all of the qubits on it work. And so we investigated that as well. The Oxford group, Simon Benjamin's group, the first author on this is Naomi Nickerson, looked at how to do a distributed form of the surface code. And also, I spent a year visiting Duke, working with Jungsang Kim, and this is work with his PhD student, Mohammed Hassan, developing a tree structure of this, where inside of this, each node runs the STEAM code. So that was sort of the first decade or so of work on these multi-computer architectures. Then there was a gap where sort of not a lot happened, because among other things, the NISQ systems were starting to come online. And so everybody was really excited to actually play with real systems. Like we can do real things on real systems. And so the issues of scalability in architecture sort of took a back seat to the immediate engineering problems for a while. But in 2022, and slightly earlier, there was a series of papers on the effect of cosmic rays and background radiation on superconducting chips. And so if one of those chips actually gets hit by a high energy particle, it doesn't physically damage the chip, but it destroys all of your quantum data in the chip. And so even if you've got a certain level of error correction in your system, if it damages all the data, you can't recover from that. Because error correcting systems depend on, generally speaking, the assumption that errors are independent, right? And they're not. So we looked at how you could build a 2-tier system where you do one type of error correction inside the nodes and a separate type of error correction between nodes, so that if one chip dies, then you can reconstruct the data off of the other chips. And that allows you, among other things, to use what's called an erasure code instead of an error correcting code, because you know where the errors actually were. And then over this last several years, there's been a really, what I think of as a fantastic paper from Spain and Delft on understanding how you're actually going to use these systems, okay? And then work from Dirk England's group, where essentially they propose a repeater tree. More work from Simon Devitt's group on how to do lattice surgery between a set of nodes. And then last year, this fantastic paper called Arquin, or Arquin, I don't know how you pronounce it. By first author is Ang, and then it's got like Sophia Kanemu and Ike Chuang and Martin Nossi, so I call it Ang and the Golden All-Stars. It's because it's got pretty much everybody on it. But somebody asked about transducers. This is a paper I highly recommend reading on the effect of transducers on large-scale systems. Then finally, we proposed a structure called QFly, which I'll talk about a little bit about later, and Shota will talk about tomorrow. And it develops from a dragonfly family structure. So, if we are going to build a large-scale system, we need to answer a set of questions about that structure. I'm not going to go through these in order. I'm going to start here. How do we do logical error corrections and logical operations between these nodes? This set of devices, or this set of proposals, assumed that error correction is inside each node. So you have one logical qubit inside one node, or multiple logical qubits inside one node, and then you're doing logical operations between them. But some of these other structures, including our own proposal and Liang's early proposal and Nickerson's proposal from Oxford, the quantum error correcting word, or the quantum error correcting block, actually spans across multiple nodes. Now you've got sort of a different set of conditions or constraints on how this system is actually going to have to work. One proposal for doing logical gates. How many of you all are familiar with lattice surgery? Only a very small number. Okay. This is a logical qubit in the surface code. So surface code. How many of you all are familiar with surface code? A much larger number. Okay. Surface code is one of the most heavily researched error correcting codes in quantum systems over the last, what, 20 years now? 20 years, I guess. Originally developed or proposed by Alexei Kitaev and Eric Dennis, I think, and some others at Caltech, and then developed by Robert Rausendorf and Austin Fowler and others into its modern form. This was done in part in my lab. So Dominic Horsman worked for me, and Dominic and Austin and Simon came up with a lot of this, the core ideas of this topic, of this concept known as lattice surgery. And then I contributed a little bit to it. And the basic idea is this is one logical qubit, this is one logical qubit, this is one logical qubit. And they're independent until you connect them at those pink qubits and make one single surface. And if you follow this, the structure of this properly, you can execute a C0 gate between here and here. It's the basic idea. So lattice surgery has been the dominant form that people have used to analyze the potential behavior of large-scale systems, well, you know, for more than the last decade now. I think it's probably the most common way of doing things. But it's starting to be supplanted by some of the newer work that's coming out in recent years, including work from Daniel Litinsky, who works at PsiQuantum, and Craig Gidney, who works at Google, and some others. But let's follow this structure for a minute and say what we want to do here is we want to execute that remote circuit on these logical qubits. Well, let's say one of these logical qubits is A and the other one of these logical qubits is B. The question is, what are we going to do at this boundary? Are we going to connect this across this boundary using this set of physical qubits? Or are we first going to make a logical bell pair between the two nodes and use that logical bell pair to mediate this same operation over here? So this is a design choice in making your system. Okay. If we follow the first approach here, we're going to need a fair amount of logical fault-tolerant memory in order to make this work. You're going to need 7 or 8 logical qubits just to buffer things up while you're doing this operation. And one of the key questions is whether you're going to purify and then inject, or whether you're going to inject and then purify, where purification is essentially a form of error detection. And injection means taking a physical qubit that encodes some data and then expanding it into a logical qubit. Okay. So you're going to purify first on the physical bell pairs and then inject, or you're going to inject first and then do the purification on the logical bell pairs. Alternatively, if you're going to do this at the physical level, you're going to need this many physical bell pairs, and then you can do this in what's called a transversal logical gate, or using this lattice surgery, or a more direct stabilizer measurement. And it's going to require high fidelity physical memory and physical layer purification. But in either case, regardless of which approach you take, you're going to wind up consuming a lot of entanglement for every remote logical gate you're actually going to execute. So, this is something I think that gets a little bit lost on the experimentalists who are so focused on getting the entanglement generation rate and focusing on maybe demonstrating this one logical or this one physical remote gate. We're going to build on top of that to actually do this in logical operations, and you're probably going to need hundreds of physical entanglements to execute one logical gate between two nodes at reasonably high fidelity. It's quite a lot of resource requirements. All right, let's see. Let's go back to that issue of the traffic pattern, which I mentioned earlier. Let's say you've got a set of nodes, and the application you're going to run requires first that these nodes talk to each other or share entanglement with their neighbors in a loop fashion, and then second, diagonally across this, and then maybe third to back to this pattern. That's the traffic pattern. That's what your network needs to be able to do in order to execute this. And it's defined by the combination of the application you're doing and also the compiler that you're actually using, or your toolkit for building all of this. And this is one view of this. This work goes all the way back to my PhD thesis in 2006. We can talk about telegate, that remote gate operation that I've talked about, or teledata, which is the just moving data back and forth via teleportation. If you do the telegate approach and you split your circuit here into two nodes right here, then you're going to have three remote gates this way. And whereas if you do data teleportation, you're only going to have two. So in this case, teledata looks better, but that's going to depend a lot on what your application is and how many times it gets used and reused and that whatnot. But if you do this approach, then you need more active management of your data as it moves from node to node. And so your software systems get to be more complex. This circuit, by the way, does anybody know what this circuit is? Are any of you all enough at the application layer that this looks familiar? No? This is an adder circuit that adds two registers together. This is as defined by Vedral-Barenko, and who was that E guy? VBE. This is the Vedral-Barenko and Eckert. So this is from Artur is the senior author on this. It was done when Vlatko Vedral was a PhD student. So that circuit dates back to the 1990s. All right. People are starting to get fidgety. Everybody's getting tired, I think. Let me go just a little bit farther and then we'll call it for lunch. All right. So I mentioned compilers. There are a couple of different approaches to compilers. The basic gate approach that's pretty obvious. But more recently, graph state-based approach, which ultimately builds on the measurement-based computational work of Robert Rausendorf. How many of you all know measurement-based quantum computing? About half, right? Measurement-based quantum computation was developed by Robert Rausendorf, I think when he was a postdoc at Caltech. But there's been a number of extensions on top of that over the years, including what's called the game of surface codes approach, which is developed by Daniel Latinsky, and then additional work on from that called the active volume approach, which comes from Google. And so there's great work there. So the differences in this are going to vary quite a bit. All right, so let's talk about network topology, and then we'll call lunch. So an obvious thing to do when trying to build out a large scale system is to take one node and give it 4 interfaces, north, east, south, and west, and then just scale this system out. Okay. That's actually an approach that was taken in classical supercomputers in the 80s and 90s. But in the quantum context, this nice, clean, pretty structure here, if we use those MIM links that I was talking about earlier, every single one of those links also has to have a Bell state analyzer associated with it. And now all of a sudden your hardware is a lot more complicated, especially because this is a Bell state analyzer. This cryostat contains the SNSPDs, the superconducting nanowire single photon detectors. I've learned to say that without stumbling. Inside that cryostat there, operating at 2 Kelvin. But in fact, inside one cryostat, you can actually have not just one Bell state analyzer, but a set of them. And so that suggests that maybe a better structure is something like this, where you have a pool of detectors on one side, on the right over there, and a whole group of nodes over here on the left. And in order to create entanglement, say, between the top node and the bottom node here, what happens is that each one of them emits a single photon. They come through this interconnect here in the middle and meet at one of the Bell state analyzers using this structure we had previously defined. And if you have built your interconnect properly, you can have not just one, but actually a set of operations all going on concurrently. And that will give you entanglement between the top and bottom. And just to reiterate, this entanglement is a consumable resource. And so the job of the network is to make lots and lots and lots of it. Now, passing through this, the most obvious structure for this is a permutation network that allows any set of these inputs to get routed to any ordering of outputs. But in fact, we don't need that full structure because we don't need all permutations. What we need is all pairings in order to make this work. So here are 2 Bell state analyzers, simplified a little bit to just these half moons here, and 2 2x2 switches. We got 4 inputs and 4 outputs, and we want to pair those. If the switches are off or straight through, we have the pairings 0, 1, and 2, 3. If we turn on one of these switches, now we have the pairings 0, 2, and 1, 3. We turn on the other switch, and now we have 1, 2, and 0, 3. So we only need 2 switches for doing this. Whereas in a common structure for creating the full set of permutations, you would actually need 6 switches in a structure that's known as a Benesch network. And no surprise, Benesch himself worked for Bell Labs back in the 1950s, give or take. So if you extend that on, Mia, say hi. This is Mia's work. This is Mia's paper from QCE, IEEE Quantum Week from last year, in which we proposed a design for a chip structure that will do this for a larger set of inputs and reduce the required number of switches that these signals have to cross by a factor of 2 or so. And so that gives you a certain level of scalability. But if you want to go beyond that scalability and get to this level of scalability, what are you going to do? Well, this thing has inside it what's known as a dragonfly structure, and this is the dragonfly network defined by the group of Bill Daly from Stanford University. Each one of these little pink circles, that's a computational node. The orange squares are switches, and you can see they're put together in a group. Inside the group, all of the switches are interconnected with the blue lines, and then the groups are connected to each other using the orange lines. So this is what's called the dragonfly structure, and 8 of the world's 10 fastest supercomputers use a structure like this. So supercomputer architects have decided this is pretty good. How do we go from there to a quantum version of this? Well, the first thing we need to do is understand what the group is going to be. You have a set of n nodes down here, which might be sensors or might be computational nodes, the switch in the middle, and the cryostat with a set of Bell state analyzers in it. And then an additional set of links that come from those other switches and go to those other switches. And when you start to scale it up, it'll start to look something like this. Okay. If you start with connection within the group, intra-group connection, key performance metric here is how many switches photons are going to have to cross between where they're emitted, and the Bell state analyzer. In this case, they cross two. Each photon crosses with a switch once. And this is intra-group communication. Whereas if you do intergroup communication, now this one crosses one and that one crosses two. So it crosses a total of three. And maybe you do a more indirect approach where the red one crosses 1, 2, 3, 4 in order to get there. So with this structure, we can say, I think pretty clearly, the way we're going to structure it, you have P nodes inside of the group. That's the group size. Some number of Bell state analyzers there. And K will be the switch radix here. And that switch radix determines a lot about the difficulty of building the switch. And then the set of global parameters is the number of groups that you've got. And ultimately that will tell you how many detectors you're going to have and how many end nodes you're going to have. Now this total structure, I think pretty clearly scales to tens of thousands of nodes, because the classical node, the classical supercomputers go to hundreds of thousands of nodes. This will scale quite a lot, but the implementation is going to be limited in practice by the quality of the implementation of your group switch. And so that's fundamental, and it's one of the key points of the architectural and implementation work we're actually doing today. And let's see. I think that's a pretty good place to call lunch. We'll come back this afternoon and we'll do a little bit more. Questions? We still have a few minutes for questions. What questions do you all have about this basic structure and about this idea of multi-computers, putting together groups of nodes in a network to solve a single problem? Yeah.
What makes this structure good? Like, what's the performance metrics that you're using to say that it's good?
Yeah. The single most important element of that structure is minimizing the diameter of the network, minimizing the number of switches that these photons have to cross. So one of the other key structures that people have been looking at, and something that was popular in classical supercomputers from the late 90s until maybe 2010 or so, is a structure called a fat tree. And fat trees are still used in a lot of data centers worldwide. And we looked at a fat tree structure. Dirk England's group at MIT has also looked at the fat tree structure, and also a group from Cisco, who I did not have on that slide of the current history. They're doing some interesting work right now on fat tree structures. But the fat tree structure is inherently multi-tier, and it means that the photons are going to wind up crossing more switches. And also in the fat tree structure, one of the key questions is where you're actually going to place the detectors. And in current technology, and this may change as the technology evolves, but the availability of high quality detectors is still a significant bottleneck to building large scale systems, and a significant economic bottleneck, because those SNSPDs are very expensive. And so we want a structure that makes very effective use of that set of detectors that's in it, and that minimizes the number of switches that those photons have to cross. And we think that this QFly based structure is substantially better than the fat tree than that, and also relative to other structures as well. Other questions? Yeah.
Okay.
So this idea of multi-computers, I guess this one is very much for data center networks. I've also heard there's ideas of like kind of like multi-core quantum computers on a smaller scale, so more like an individual computer that consists of multiple cores. What are some of the architectural differences you would see between like this data center network type multi-computer and more of a smaller local scale quantum multi-computer?
That's a good question. And for example, I don't think I have it in this slide set, but it's probably in some of the other slide sets that are linked to from this or the first set. But IBM is actually building systems and working towards systems that have not just this two-layer simplified structure that I've talked about here, where you have inside the node communication and outside the node communication, but they're working on a multi-tier physical interconnect structure. They call them L couplers and M couplers and C couplers or something like that, different kinds of couplers, where they will have two chips, and you have on the chip, you can connect directly to nearest neighbors. They also have bridges that will connect to farther qubits on the same chip. They have two chips that can butt together and they'll just solder a wire across them, or two chips that are a little farther apart and connected via waveguide. And that can all be inside one refrigerator, and then they'll have a separate structure that actually connects it to longer distance ones. So you can end up with this multi-tier structure. And always the engineering trade-offs need to be ultimately numeric, because all the quality of each of these detectors or couplers and the rate at which each of those couplers can operate is going to be different and is going to vary as the technology evolves. And so where the sweet spot is for building a system today, that's going to move over the years as the systems evolve. I don't think I have it here, but you may have seen pictures of what the IBM guys call the System 2 systems, which are these nice, they've got nice 3D renderings of these, and they've got this beautiful hexagonal structure then supported by a set of large 19-inch racks, this nice 3D rendered structure. And then somebody took a set of those and then basically on top of it used PowerPoint and drew a set of lines and said, we're going to connect a set of these, right? So, and that actually roughly corresponds to the amount of energy they put into the two levels of the operation. They're building to scale one individual node as much as they can, but they still don't have a really strong story on how to connect multiple refrigerators over a significant distance for this. But for a while, IBM was talking about optical structures exactly like what we're talking about here, but IBM has decided that the optical transducers are very hard, and so they are working instead toward a structure where the separate refrigerators are connected via large vacuum tubes and still using microwave photons between nodes, which they have talked about publicly to a certain extent. It's very interesting. That trade-off is going to, we'll see which one actually works out in that sense. But other technologies besides superconducting have a little closer connection to optical, and this kind of switching structure that we're talking about seems very obvious. Other questions? Yeah, we're here.
Have you tried to look into replacing SNSPDs by SPDs, but relying on post-selection to make everything work?
So sorry, what's using post-selection how?
Yeah, just post-selection in the sense that you use some unserialized qubits to, know what's going on inside your system, and then you post-select and you discard the one that you are not interested in, and you keep the ones that they are working properly thanks to these auxiliary measurements.
Yeah. There are different roles in which the ancilla can take in a structure like this. I didn't talk about it very much, but all of these structures that we're talking about here are highly probabilistic. And so the generation of the single photons is probabilistic. The measurements at the Bell State Analyzer assume they're probabilistic based on loss in the channel, as well as the Bell State Analyzer itself being probabilistic. And then purification, which we'll see this afternoon, is also a probabilistic operation. And so all of these tiers build up to the point where driving the system and running the system is going to be a long series of operations that are conditional on previous operations. So yes, there's a lot of stuff that can be done there. And obviously, once you get all the way to the logical level, there are one common structure for decomposing the Toffoli gate in applications into 2-qubit gates involves a measurement after executing one particular gate, and then you have to apply a correction, either a T or a T dagger gate afterwards, depending on the result of a prior measurement, and then that adds more indeterminism to the forward operation of the system. So that's actually an area where I think there still needs to be a huge amount of work in the software and hardware control systems to allow the feed forward operations and dynamic decisions about what the next set of operations are going to be. And it's something, that's going to take a tremendous amount of hard work. Any other questions before we go to lunch? All right, Dr. Elkus.
Thanks.